I got this at Cash Converters for $50 and just opened it up, and it's actually a March 2022. The bottom shell was April 22. The circuit board is 2019 revision 0.7, 2019 June 27. 2 precision shunt resistors coming off the negative rail, B-, going into there and then going through the shunt resistors and then back into wherever. Well, probably going under the board and then coming out here, power minus. Losing track of showing frame. And on the positive rail, there's a thing here. I'm going to have to look that up in a second, but it says has 30 amps KO2. It looks too small to be a power thing, but maybe it can handle the... Well, I'm expecting... It says 30 amps, but I'm sure Makita batteries go harder than that. And yeah, got lots of silicon on top. This side has quite a bit of bubbles. It's sort of spongy. And then we have CN1 here. So this third pin is actually 2 pins. CN1, and I can't see a marking for this other one. And you need to short circuit these 2 pins to activate the battery. So as you insert the tool, touching these 2 pins together is what wakes the battery up and tells it to start monitoring everything. Oh, and they've got the little air vent. That's pretty clever. It goes right into the center of the battery. This is a N-channel MOSFET. It's 40 volt and I think 0.45 milliohm. This is the main chip. It's both a microcontroller and an analog front end in one thing. It's got an embedded MCU and it's also got balancing functions and current sensing and analog pin for the thermistor, and a pin that can drive this thing, which is a fuse. So it'll pop if the current exceeds 30 amps, but this device here is also capable of short-circuiting a pin, which you can't really see here. There's a bit of a trace going up there if I haven't got the lighting wrong. But if you short-circuit that, there's a little resistor in there that will then cook the fuse itself. So it's a fuse that can blow if it goes over current, but you can also remotely blow this fuse if you want to. And then we've also got these shunt resistors. There's definitely a few components under there. Look like largish components, maybe. Definitely some stuff in there. You can see a whole lot of siliconing in there, but it's probably some MOSFETs or some other stuff. Other little maybe logic circuits. This is the main chip, Renesas RAJ 2480, 2 to 5 series lithium battery, fuel gauge, blah 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 blah. It's got a little microcontroller as embedded inside of it. It's got the current sensing here, measuring the voltage either side of a current shunt. These are the battery cells. It can do up to 5 cells, so this chip is almost certainly not on XGT batteries. And it's got the cell voltage monitoring and balancing going on. It's got its own little drivers for it. And it's got a FET driver for high side N-channel MOSFET, which is interesting. Oh, and there's the fuse driver, by the way, because we've actually got a low side N-channel FET here. I'm pretty sure it's low side because, I mean, this is B+, and this is the positive terminal, and you can see the exact trace going through there, and there's no extra MOSFET. It's not getting directed down here. The positive is not doing some little random thing where it shoots off under the board to this MOSFET and then comes back again. It doesn't make any sense. I'm pretty sure that this is on the ground rail, so it's a low side MOSFET. Now, the fuse. Up here, this little 30 amp doodad is a Dexerials, which is also a Japanese company, fuse. It's that's like the little body diagram of it. So it's got a little heater resistor in there. Fuse resistance 1 to 2.5 milliohm. Rated current 30 amps. Rated braking capacity 80 amps. Yes. Oh, and finally, the big N-channel MOSFET is an ON-Semi. It's an American company, so that's the odd one out. Power MOSFET N-channel, 40 volt, 0.45 milliohms. And then the rating is 558 amps, but that's kind of a BS rating. And they say it down here. 558 amps is keeping it at 25 Celsius, which you would need, you know, liquid nitrogen to do. The realistic rating is this sort of 394 amps at 100 Celsius. And that depends on having a very good heat sinking. So here it's got junction to case resistance, so thermal resistance, theta JC of 0.61. So if you can achieve that, which would be a very good heatsink and very good joint bonding to it, then yeah, you can get your 400 amps. But without that, it looks like you can only get 56 amps. The top of this MOSFET is exposed. It does not have silicon on it. Most of the heat sinking is actually underneath it, and I think a lot of these little pins around it are kind of to act as a bit of a heat sink. Oh, and then they're Samsung 25Rs, by the way. We are looking at what the pins on the LXT battery do. So we've got yellow meter connected to the yellow pin, we're going to call it. It's the outermost of the third pin. Blue meter's connected to the green wire, and that's the innermost or deepest of the third pin. And this one here, white, is pack voltage. LED comes on but nothing happens. If you squeeze it quickly, you get a bit of a motor turn. What happens is this third pin slides in, and I'm pretty sure it touches both pins at the same time. So effectively short-circuiting the yellow and green pins. And we'll just do that now. And that brings green up to 19.8. Let's bring it back. Well, actually, let's just show. This is unexpected. I don't know if it's because I'm a moron, but if I measure the voltage between the two pins, it activates the battery. At least it did last time. Yeah, there we go. So I don't know if it's a capacitance-based thing, but yeah, there should be no current flow between them. Anyway, so this meter measures 0.62, 0.63 volts between the two pins. Let's see what happens when we connect green to the tool. I'm pretty sure this will run. Yep, pretty sure yellow to the tool also runs. Yeah. Huh. So when green is connected to the third pin, we get 1 volt across those two pins between the green and yellow. Yeah, so that's the third pin on the tool. It's got a kind of hook shape. So it looks like it contacts the outermost pin when it's getting inserted, and only contacts the innermost pin, which is the green one, when it's fully inserted. So it contacts the yellow one first, and then I think it contacts both of them, and then it only contacts the innermost one. It may be contacting both of them at the same time, but it doesn't make sense for it to be a hook shape if it's designed to contact both of them at all times. I think it's designed to contact yellow, then both, and then green only. So I just did a little test off camera. When you touch these two together, blue comes high and stays high for a minute, and then turns itself off. And it's also the same. If you connect them together, leave them together, that stays high forever, pretty much, and then you disconnect 1 minute later, that comes low. We just saw that the blue pin, the deepest pin, will turn on at just 1 volt. I didn't think to check what happens if I just short it to ground. Will that turn it on? Nope, shorting to ground will not turn it on. 0.058 volts, is that enough to turn blue on? Ooh, we get, well, no, okay. Go for 0.1 volt. 0.1 not enough. 0.8 does not wake it up. 0.9, should be getting close now. Huh. What on earth happened then? Okay. So it looks like 0.9 volts is enough. We're looking at what the current draw from the deepest pin is. So that's measuring the current, and that's measuring the voltage of the deepest pin. 1 mega ohm gives us 19. 10k. 1k was 6.45 volts and 6.5. Alright, 2.2k, we get 10.2 volts. Okay. Yeah, I don't know how well you can see that, but it's working pretty well. Don't tell me I cooked the LED. I think I may have cooked the LED. Buzz. 8 milliamps. We're going to look at how much current flows between these two communications pins and the tool. So this meter is currently measuring the current through the blue/deepest pin. And if we connect that to the tool, nothing's going to happen because we're at virtually 0 volts. We squeeze the tool trigger. Oh, and it works. I was not expecting that. Okay, 0.191 amps. Let's go to micro. 188. 188 at rest. Now there we go. So it turned off, and that's good. Absolutely 0 current flow. Okay, so now that is measuring the voltage on the tool pin. Okay, so the tool outputs. Okay. The scope gives a pretty steady 12. Okay, we've now got green also connected. And we go to 19. We've got a power supply connected to the tool pin. So this meter is measuring power supply because the power supply has a terrible voltage thing. So we're putting 18.4 volts onto the tool's third pin. And the pack voltage is 20.4. And that allows it to start. So if I drop it down to 18.3, okay, that also works. 18.2, that's borderline. So I don't know if it's a 2 volt difference there or if it's measuring the difference between these ones. That's like a 1.6 volt difference. Around 1.5 volts. And it starts. If I turn it down, Also 1.5 volts. Okay, so it's measuring 1.8 voltage difference between the battery pin and the tool pin. And that's not enough. Oh, sorry, that's too much. So let's increase it. .6 looks like it's just enough. It's like really borderline. I think it's so now if I turn the voltage down, the voltage difference increases. So at about 1.57 volts difference between it, the tool cuts off. We're looking at what the tool does when it gets to low voltages. 12.93 won't start. 12.95 will. Now, the other thing is, you can go, once the tool has started, it will let you go lower. So 12.9. Turning the voltage down. That's well below any kind of cutoff, right? The tool is not recognising pack voltage. Whoa. Let's see if we can get below 6 volts. Alright, 6 volts seems to be its minimum. That could well be an electronics thing, or it may have a low voltage cutoff, but why would you put your low voltage cutoff at 6 volts rather than 10 volts or so? We've got a little voltage divider going on here. So this is the voltage going into the tool on the positive and negative pins, and that's the voltage on the tool pin. We've got over 13 volts at the tool, but we have less than our 12.95 volts on the T-pin. And the tool will start. It seems that it's a voltage difference rather than a threshold. That's a 2 volt difference. Okay. 1.9 volt difference. 2 volts is too much. 1.9 works. Less than 2 volt difference works. Greater than 2 volts does not work. 15. 1.4. 1.7. Oh. 15 will do 2. Will not do 2.2. It'll just work at 2.05. I keep going the wrong way. Okay, will not work at 2.15. Does work at 2.05. 2.07. 2.01. Okay, let's say 2.01. I think the threshold is around 2 volts, but it's not precise. Unless the tool is over 13 volts. 2.2. Nope. 2.08. Will start. 0.15 will start. Oh, just. So it seems to very slightly increase as the voltage goes down. So I'm going to get the tool running and then increase the delta. So we're increasing the delta. We'll just go straight to 1. So we're expecting a 2 volt delta to create shutoff. There we go. .01, 205, 2.05 delta. I'm running it down at 10 volts and I'm increasing the delta. .97, 2.01. Ooh. Okay, so 2.3. I want to look at how the voltages on the battery pins change with temperature. We're currently at 24.5 Celsius, 19.74. So I'm pretty sure this outer pin is pretty much always the same as positive, 20.372. Now, differential voltages. This one is going to be 0. This one, which I think is the critical one, is 0.6205. And then these two. And this should be the same. Alright, now we'll go put it in the fridge and see what happens. We've had the battery in the fridge for 2.5 hours. We're going to see if that changes that pin voltage. I'm not expecting any difference. I think the 0.6 volts is just due to a diode. So pretty much the same. It's like increased by 27 millivolts from being in the fridge for 2.5 hours. So I don't think there's any thermistor information there, unfortunately. We're redoing our rundown test because the camera cut out. This is measuring pack voltage. This is measuring voltage difference between the deep pin and positive. This is measuring absolute voltage of deep pin. This is measuring absolute voltage of the shallow pin. These 2 meters measure a tad higher than these two, which are probably more accurate. These ones are about 0.06 volts higher in general. I'm going to give it a 7 amp load and take measurements every minute. Okay, we're coming up to the end of our capacity test. We're at 37 minutes, 13 volts. It's going to cut out at about 12.5 volts. This is set to trigger when the deep pin drops below 5 volts. And it's going to be a 1 millisecond division. We're going to try and see which one drops first, the deep pin or the shallow pin. Okay. The deep pin definitely dropped well before. Well, hopefully we saw something happening on these. So yeah, again, deep pin goes to minus 11 volts. Starting at 94 ohms, and we're going to drop down to 22 ohms. So this will be 94, 200 milliamps. $276 milliamps, no luck. 50 ohms, 400 milliohms, nothing. Okay, we'll do 44. 24 ohms, 450 milliamps, not waking it up. Interesting. Straight to 22 ohms. There we go. Alright, 22 ohm or 800 milliamps definitely wakes it up. I don't know if this means anything, but I'm just looking at the resistance between the pins on the tool. From ground to the third pin is 263 kilo ohms, and it doesn't change when squeezing the trigger. From positive pin to the tool pin is a lot. 144 mega ohms. If you squeeze the trigger, it goes to, I'm assuming it's filling a capacitor, so we have to wait for it to level out. Still going. 84. Well, still very slowly increasing. It's probably 85 kilo ohms, or thereabouts. Okay, resistance between positive and negative on the tool with the trigger squeezed. Oh, okay, I shouldn't have done that. Anyway, same deal, filling a capacitor. I think it's around 25. Oh, 100. What the? The purpose of this is to see if that third pin was a thermistor pin at one point. I think on the new batteries it's a semi-digital pin. They pull it low whenever the BMS detects something, but I think on older batteries it was a direct connection to the thermistor. So I'm trying to look at what resistors are between, say, the positive and that, or that and a thing, to figure out which side the thermistor is on. Presumably, so it's you'd think the thermistor would be between the, at least in the battery, between the third pin and ground. And that way you get your, whenever the voltage between the positive pin and the third pin goes over 2 volts, then it stops. Okay, so we're getting 28.7 kilo ohms with the trigger squeezed. And with it released, it's something crazy. Mega ohms. And if we change it around, what we get? Oh, it's completely different in that direction. Okay. Well, there's clearly a diode there with, that's measuring from the third pin to the positive pin. And trigger doesn't change it. When we switch it around, so was it 85 mega ohms? Yeah, 140-ish, but dropping a lot. When you squeeze the trigger, 300-ish kilo ohms. So there might be diodes in some of the tool pins. So from third pin to ground, we've got 1.44 volts, so maybe 2 diodes. Other way around, nothing. Oh, squeeze the trigger, nothing. And I'll just put it back to how it was, 1.44, squeeze the trigger, nothing. Okay, from positive to negative, we seem to have a 1.1. That drops to 0.82. If we flip them around, I think it does something weird where the voltage climbs and then overloads. Oh no, nothing. It says yes, there's a diode, but it climbs and then overloads. From tool pin to positive, nothing. Even when squeezing the trigger, around the other way. nothing. But I think the interesting one is third pin to ground, 1.44. That seems like 2 diodes. We're looking at the voltage on the third pin of the tool. I'm calling it the T pin. So we're going to use this meter for both measurements. It's currently measuring, we're using a power supply to put power into the tool, and nothing will happen because there's nothing on the T pin. And if we put this on the T pin, nothing, but if we squeeze the trigger, we get 12.384. 10 volts. So we have 12.384. Now we're getting 5.672. 5 volts. Five volts gives 2.38. 15 gives 9.027. Okay, we're coming up to the end of our test. We're doing a rundown test of the battery at 7 amps. We've got our scope set up. It's 10 millisecond per div, and we've only got 14 divs, and that's pretty much the max memory of this cheap little scope. So we're only going to be able to capture 140 milliseconds. Previously we did not capture the difference. So the deep pin goes low before the positive pin, and we want to try and capture what the delay between that is, but we've only got 140 milliseconds, and going off the video it could be up to 500 milliseconds. So hopefully this works, and we'll see blue line low and then sometime later yellow line low. Oh, well, I don't think we caught anything, did we? That's a shame. So blue went low, but we're not gonna get yellow low. No. So it's more than 140 milliseconds. Okay, we're back. We're basically running the scope in like manual mode. It's 100 milliseconds per div, so more than one div. Well, basically 2 divs is going to be what we previously saw. We're going to start it at, we had it in the chart just a little bit, it's up to 16.6 volts. We're just going to start it at 3 amps. 7, alright, any second. Oh my god, I went too early. Okay, we're going to try that again, but without me being stupid. This time I need to remember not to panic when the blue line goes low. Let's just hope that it times itself. Oh, what? Okay, we're going again. This time we're going to go at 1 amp and see if that changes the delay between deep pin going yellow and the main pin going yellow, positive pin. Oh, here we go. Okay, quite a big difference. Deep pin has dropped well before. So does the deep pin drop at like 12.7, and then I think the positive pin drops at maybe 12.5? We're getting close. Or is it going to keep going? Going to go below 12.5. Damn! This is kind of what we saw with the Sauron Makes video, where he went down to 8 volts. Alright, we're at 4 amps and Sauron got... so silly saying Sauron. Sauron got low voltage cut out at 8 volts with 4 amps. And that looks like what we're going to get. Okay, so there's low voltage protection, but it's kind of funky. That is really weird. This is why it's so there's so much conflicting information about whether or not these things have low voltage protection or not. If it goes down to 7 volts, then I think I'm going to have to say it. There we go. We're off. Okay, we are discharging at 4 amps. This meter is measuring the D pin again, and this meter again, same meter as yesterday, is measuring the negative pin to the positive pin. And this meter, which we've just added, is measuring true ground onto the battery to the positive pin. So there's shunt resistors and a MOSFET between there. So we're going to see if there's any sort of difference going on there. I'm thinking that potentially the MOSFET is maybe slowly closing off, and that's what's causing this to go down to low voltage, but maybe it's still cutting off at 12.7. So we're going to see. So we should see blue go down. Yep. So far, no real change in these voltages. Okay, so the MOSFET does not look like it is slowly shutting off. It's just that lower currents, the BMS lets it go lower. Yeah, so the MOSFET is definitely not slowly turning off. These two voltages are the same, so nothing is happening across the shunt resistor or the MOSFET. 8 point... Oh, it's going to go... Oh, there we go. Finally stopped. We're doing another rundown test, this time 5.5 amps. We're now powering this load cell with a Milwaukee M12 battery. And that's to try and reduce any sort of mains hum that seem to be doing weird stuff. I don't think it's important for this test, but for some other tests it was giving me some problems. 4 amps went to 8.28. Okay, here we go. Drop, drop. Okay, so 5.5 is instant. Continuing our rundown tests, this time 4.75 amps. Low voltage kicking in. Alright. Oh. Okay. So, looks like 4.75 is still at that threshold, below or above the threshold, depending on how you want to look at it. Here we go, 8.654, about 8.4. Right. Alright, rundown test again, low voltage protection, 5.12 amps. Here we go. Oh, okay. That triggered it straight away. Doing another rundown test, 4.94 amps. Here we go. Nope, it's going to go down. Looks like 5 amps is our threshold. Oh, and we're off. Alright, low voltage protection test, 5.03 amps. Hopefully this is our last test. I'm hoping this will have just a half-second delay. 12.69, there we go. She's gone. Alright, 5 amps it is. We're doing one last test, going at 4.98 amps. But when the D pin, which is the blue line, drops, if the low voltage protection hasn't kicked in and yellow stays high, then we're going to increase the load and see if going above 5 amps will make the low voltage protection kick in. So we're about to see D pin go low. D pin's low, low voltage protection has not kicked in. Okay, 5.08. Okay, as soon as you go over 5 amps, low voltage protection kicks in. There we go. This is probably going to be a waste of time, but I'm going to try and measure the resistance of the shunt. 10 amps gives us 2.5 millivolts. We're going to get shut down soon. 11 amps. No, won't let me go to 12 amps. Okay, 2.5 millivolts at 10 amps divided by 10.25 milliohms, which is kind of what they read. They read R50M, which I haven't been able to find, but that logically is 0.5 milliohms, and there's two of them in parallel. So yeah, 0.25 milliohm shunt resistor. It's pretty low, and it's quite impressive that they're getting probably 10 milliamp resolution or better. We're testing what the activation current is. This is 250 milliamps, 300 milliamps, 350. Only got 30 seconds to do this. 400 milliamps, 490, 500, 510, 520. Okay, 530. What we found is that it takes a minute for the battery to turn itself off, and then if you wait another minute, it goes into a deeper sleep, and it takes 5.02 amps to wake it up. But from that minute, from this turning off, in the minute after that, it's a much lower current to reactivate it. So it looks like it's around half an amp. We just got then 530 milliamps. We're going to start at 400 milliamps. Here we go. Doesn't turn on. 410, 20, 30, 40, 50, 460, 470, I've only got 30 seconds before it goes into the deeper sleep. 480, 490, 500, I've got 20 seconds left. 510, 15 seconds to go. 520, gonna leave it there. Okay, looks like 520 milliamps. Alright, we're looking at what's the minimum current that is needed to keep this battery awake. We're currently running at 510 milliamps, and it's kept it awake for at least 2 minutes. We're going to let that go up to 3 minutes, and then we're going to turn it down. Spoiler alert, it turns off at 500 milliamps, and it does so in exactly 1 minute. So when that hits 3 minutes, we're going to turn this down to 500 milliamps, and then I'm pretty sure at 4 minutes we'll see that drop. Alright, coming up to 3 minutes, we're going to turn it down. It's now on 500 milliamps. So coming up to 4 minutes. And there we go. Deep in drops exactly 1 minute after we went from 510 milliamps to 500 milliamps. We are looking at if there's any communication between battery and tool. We've got the battery wired up to the drill, the DDF083, and we're monitoring it with our scope. And when we squeeze the trigger, so yellow is irrelevant, we're just looking at the blue here, and blue is the D pin. When we squeeze the trigger, it just goes high, and that's it. You do not see any communication of any sort. So it is flat out lies from Makita that there is digital data being transmitted. all it is a stop-go signal. Looking at what happens when the tool starts with a bit finer detail, we see that there's sort of a bit of a two-stepper going on. So this is 1 millisecond per div. So the first thing that happens, we get 4 milliseconds, sorry, 2 milliseconds per div. We get 4 milliseconds of it being at about 11.8 volts. Then after that, it goes up to, I think, 18 volts. I mean, this thing's pretty inaccurate when it's measuring voltages, so it says 19 volts. So yeah, it seems that's, I guess, the trigger coming on, and then 4 milliseconds later, the battery detects it. So when you squeeze the trigger on the drill, the T pin on the tool goes up to, I think I measured it like 12.6 volts or something, but it drops as the supply voltage drops. So the tool is bringing the T pin high, which is signaling to this, and then 4 milliseconds later the battery is bringing the D pin high up to 18 volts, and then that can start the tool, because the tool needs the D pin to be within 2 volts of the supply voltage. Here's another run that I just did. It's similar, 4.2 milliseconds. I got it at 1 millisecond per div, and you see a similar sort of bump and then higher. So I'm pretty sure this first section is the drill bringing it high, and then it goes higher as the battery goes up. We'll do another one live. So that voltage has just dropped, so we'll see it happening here. Are we running? Yeah. So yeah, we get the exact sort of behaviour. It's a bit of a bounce at first, and then this goes high, and a little bit different timing this time. 3.76 milliseconds. I'm going to disconnect this. So now the tool is not going to be seeing anything, and it shouldn't get that second pulse. It should just go up to about 12 volts. Yeah, okay, and we don't get the little ringing either. Oh, no ringing at all that time. Interesting. Huh. And what's the timing like this time? 4.3 milliseconds. Alright, we're looking at the low voltage protection when we're connected to the tool. We've got a horrible little setup here where the drill is powering a crappy little pump and just recirculating water. It doesn't work very well. We only get about 6 amps, and we need to keep this above 5 amps in order for it to work. But the important thing is that that stays above 5 amps. Otherwise, we've got these guys to try and clamp the spindle a bit. So I'll Velcro the trigger on. And we're getting current dropping rapidly. So we might have to provide some extra. There we go. Okay, we got some sort of cutoff. Now I don't know if that's going to let me go again. Nope, it's not. So the tool is now bringing this up to 7.6, but it's not activating the battery. Battery's at 13.8. I'm just looking at the thermistor. I was expecting an analog voltage. I've got these 2 needles poking through the silicone, just in there, to touch the thermistor. And brightened up a bit. And we are getting digital pulses on the thermistor. So yellow and blue are just measuring different sides of it. I don't know why I'm doing that. I should probably set up one to measure across. Well, anyway, so that's the voltage from ground to either side of the thermistor. And it's giving a pulse of a bit under a volt. And it's like 2 pulses, 14 milliseconds between pulses, and 56 milliseconds between each pair of pulses. Let's get yellow to measure the voltage across across the pins. The voltage across the pins was very... oh god, I broke it. I appear to have killed this battery. I somewhat shorted the thermistor, and now the battery has pretty much locked itself out, I believe. Have a look inside and talk about the stupidity that I just did. Yeah. So every couple of seconds we see a flash on that. But for some reason, there we go. And the reason was because I'm an idiot. I was measuring the voltage on these 2 pins here, the thermistor pins. So it's either side of a NTC thermistor most likely. And I had to measure it on the scope, and I was measuring the scope from ground to the lower pin and from ground to the higher pin. And then I thought, oh, wouldn't it be good to measure the voltage across the pins? So I moved one of the leads from ground to the other side of the pins, but that created a short circuit because the 2 probes share a ground. And consequently the battery has recorded that as a severe overtemperature and locked itself out. It will not work on the tool, and the charger gives an error. So on the tool we get light but nothing. On the charger, yeah, so I don't know if that's visible, but it's flashing between red and green. So I'm pretty sure this battery is permanently dead. The BMS has detected, or thought it detected, a severe overtemperature and has said, no, I am not letting you charge or run on a tool. Which is kind of fair enough if it thinks that the battery has been up to, I don't know, probably a couple of 100 degrees Celsius if you completely short circuit the thermistor. This battery's dead. I don't think I'll be able to revive it. That's going to be pretty much impossible. And I'm going to have to find a new one. All in the name of science. Okay, so I bought 3 new batteries. This is the dead one, just 2021. And fairly similar circuit board. In fact, nearly identical. About the only real difference is the different shunt resistors. Now, 3 amp hour. This is a 2017. Probably bringing it out of focus there. And it is definitely a different circuit board. So this is prior to the 2019 update. It's similar, but different. There is no MOSFET. We have a pair of M50 50 milliohm resistors. I don't know, I'm gonna have to have a look, but it looks like a similar-ish chip. The Renesas chip was, I think, 2017. This board is Revision V 0.9 2015 December. One of the major differences is balancing leads. We can see coloured insulated wires for the balancing leads, whereas in this one it's now just part of the tabs that are spot welded on. 1.5 amp hour, and this guy is a 2013, so this would have been one of the first star protected batteries. 1.5 amp hour. It's using Samsung 15Ms. So very different circuit board, a lot less going on. We do have down here a little separate board, but I took it off and pried it up. There is no MOSFET under there. When you look underneath, you can see some shunt resistors, and that's it. So this is a shunt resistor, and then these two little terminals coming in here are for getting the voltage measurement across it. So yeah, much simpler board. It is a 2012 board. Okay, BL 1815N and 1830. So this board was used on the 3 amp as well. This may be one of the OG kind of star protected boards. Now the spring actually stays on. They've got a little sort of nodule there that holds it on, which is a much nicer one than these ones where it just falls right off. Okay, we finally got there, and they are Samsung 15U, which I had not come across before. I'll have to have a look at them. Okay, we're looking at battery 3A and trying to see if it has low voltage protection. I suspect it does not. I'm going to be doing 7 amps. We're starting at 15 volts, so it shouldn't take too long. Wow, that voltage plummeted. This is our... okay, there we go. So that hit that. Oh, that voltage is absolutely collapsing. Okay, let's stop that. Alright, we're just going to see what happens with the cutoff on the tool. Our previous test showed the pack voltage plummeting to 0. And this, the D-pin voltage, went to 0 at about 8.4, 8.3 volts. So I want this to cut out at 12.5, but previously we saw it went much lower. Coming up to 10 volts, which is where Milwaukee cut off. Going past Milwaukee. What are we going to do, 9.5? 9.2. 9.2 volts. And now it won't let the tool run. We're looking at what the turn-on current for the 1.5 amp hour battery is. It's currently at, and then it turns on, 1.11 amps. That is so weird. Previously we found 1 amp did not keep it awake, so let's go for 1.05 amps. Nope, staying on. We'll leave it there for 2 minutes just to be sure. Alright, that's 2 minutes. Let's go down to 1.03. That's a minute. Let's do 1.01. Did a minute. Let's do exactly 1 amp. Now previously this did turn off after a minute. Okay, there we go. At exactly a minute, 1 amp turns off. Okay, we're looking at turn-on conditions. At 1 amp or more, it will turn on after a minute. But we want to find out what its sort of instantaneous turn-on is. So we've got to ramp the current up, but we've only got a minute to do it in, because once we go over 1 amp, it's going to turn on anyway after a minute. Start the timer. That's 1 amp. 2 amps. 3 amps. Okay, so 3 amp gives us an instantaneous turn on. Alright, we're going again. We're at 2.2 amps and 30 seconds, so better hurry. 2.3 amps. We know 3 amps turned it on. 2.4 amps. 2.5 amps. 2.6 amps. 2.7 amps. 2.8 amps, but I don't know if that was it turning itself on after the timer. We're going to start straight at 2.5 amps. I think it might just turn straight on. Okay, 2.5 amps. 2.6. 6.9. 2.7. 2.75, 2.77. Alright, we are looking at low voltage on the 1.5 amp hour. We have gone below 12.5 volts and this is still there. What I'm expecting, we're only going 1.1 amps. I'm expecting this to go down to around about 9 or 8 volts because that's what the 3 amp hour did. And then we'll see this cut out, but we will not see that cut out because there is no MOSFETs in there that can cut it out. Alright, getting very low, down to 9 volts. There we go, cut out at about 9.2, and this does not cut out. Alright, I want to see where the voltage cutoff is on a per cell basis. We're currently sitting at 17.7 volts. Yellow line is pack voltage, blue line is the D pin. We're going to give it 2 amps. Looks like it's either going to be this one or this one going first. Alright, I'm bored. Let's crank this up. 4 amps. The battery can basically time out and this will go low. Ooh. Hang on, a little bit down below. Oh! We are looking at the 1.5 amp hour battery and looking at its thermistor. Same as the 5 amp hour that we killed. It's a double pulse and there's 124 milliseconds between the double pulses. 16 milliseconds between the double pulse and then 124 milliseconds out. It's currently sitting at 720 millivolts in amplitude. But in there, I've got 2 needles. They are sewing needles. And they're being held on the 2 terminals of the thermistor. So the 2 terminals of the thermistor, there's a top and a bottom one. And the scope is measuring across those 2 terminals. It's measuring an amplitude of about 0.69 volts. All the voltage to drop under heat. At least that's what it should do if it's an NTC. Okay, there we go. Temperature's dropping rapidly, or the voltage is dropping rapidly. So I don't know if you can see that, but we've gone down to very low numbers there. 440 millivolts. So it's probably quite sensitive. The temperature of the board, it's like 91 Celsius. I got stuff fairly hot then, so let's not do that anymore. The thermistor is underneath, so it's not getting the same heat. It's harder to heat that up. Okay, we're going to try bridging resistors across the thermistor to see what happens. Alright, we're going to start with 1 mega ohm. 1 mega ohm has virtually no effect on the voltage. 330 kilo ohms, no effect. I think 100 kilo ohms. There we go, we see some action there. Well, we've got a trim pot here set up to do 20 to 10 kilo ohms. It's currently on 20. Oh, there we go. Alright, we're back. Doing the thermistor again. We're bridging 4.7 kilo ohms across the signal. 4.7 kilo ohms. Interesting. 4.7 kilo ohms is still too much. Alright, we're awake. We're giving it 2.2. And that drops it. And I strongly suspect that we won't be able to wake it up. We can see it's rebounded straight away, but we can't reawake the battery. The battery's locked itself out, so we need to put it back on the charger. Okay, we're back this time with our second 5 amp hour battery. We're pulling 2 amps from it in order to keep it awake and to see if triggering the over temperature will trigger the shut-off protection. Okay, 2.2. Will this cut the power? It will not. 2.2 is not enough. We're going to have to give it 1 kilo ohm and pray that it doesn't brick our battery. 1 kilo ohm. Will it cut the power? Alright, we're trying that again, except this time 2.2. That is not cutting the power. We know that 1 kilo ohm definitely does cut the power. Touching now. And that's cut the power. Yep. Current went to 0. Battery indicator is flashing. So yeah, over temperature, this battery will 100% protect itself from over temperature. That's good. We are looking at the DLM815. It is a torch and it is a 2-pin device. And we're going to look at its voltage limits. This is voltage, this is milliamps, current flow. So we turn it on. It works, 100 milliamps. And then we're going to go really slowly here. And the current will the torch will cut out at 13 volts exactly. 142 milliamps. Let's go to 12.99. That's gone. Now it does another weird little thing. If you drop it down to, I'm not 100% sure, there we go, what the sort of thing is to get it working, but it works down at 8.8. Okay, now that the current stabilized, the voltage is coming up, and it cuts out at around about 10 volts. I'll go slowly. 9.9. Anyway, it seems like once the voltage is below a certain thing, all the safety things just basically get ignored. But once you come up in voltage, it trips the safety again. So about 9.9, particularly gain to take it much past 24. So 21, its maximum, is the maximum the battery can ever get to. Okay, we may have hit a safety there. Yeah, okay. We didn't kill it, it's an actual safety. That's good. $23.5? Yeah, 23.5. Alright, we are testing whether or not the battery protects itself from overcurrent. We have our scumbag resistor here, which is just a whole lot of Constantan wire, and we're going to plug it into the battery and measuring different pins. Oh, and also we can adjust the resistance by short circuiting the 2 strands. What are we getting? 30 amps. That's not very good. Oh, something smells burning. Short circuit. 34 amps. Something's getting hot, I can smell it. 36 amps. 38, 34. Well, the Constantin's glowing. 39, 40 amps. Damn, we're gonna have to add some more wire. Okay, second attempt. We've modified our resistor a little bit, added a few more strands, we've used up all the wire. Let's see what happens. 57, 55, stay still you mongrel. Okay, 55 amps, we're cooking. 61, 70, 78, 80, 90. Did anything happen then? Okay, let's stop that. Okay, last attempt. We're just going to try and give it 90 straight up. Alright, 53 amps. Let's go straight to 90. Okay. Oh, there we go. I'm pretty sure we tripped low voltage then. I don't think there's an overcurrent.